It is the only connection between machine and earth, a thin black line dictating the fate of tons of steel. This is the soul of movement, the single point of contact between a vehicle and the road. Every year, our world produces an immense 2.5 billion tires, a figure more than 7 times the entire population of the United States. The journey begins with milky white latex dripping from tropical rubber trees and ends with the tenacious grip holding a Formula One car steady through a high-speed turn. Each tire is a composite marvel, constructed from dozens of layers bonded together to withstand incredible heat, pressure, and friction over hundreds of thousands of kilometers. Whether it's a 600 horsepower supercar or a humble family sedan, all that power means nothing without a worthy set of tires. This seemingly simple ring of rubber controls everything: how a car carves through a corner, how quickly it can brake, how stable it feels on a wet and unforgiving road. Behind it lies a global industry operating in over 180 countries, where thousands of factories work ceaselessly to meet the demands of nearly 1.5 billion vehicles. This colossal effort drives a market valued at an estimated $320 billion. At the absolute pinnacle of performance, a set of Formula One tires may only last between 50 and 100 kilometers, with some barely surviving a single blistering lap before being discarded. Here, a tire is the fine line between victory and disaster, between a flawless launch and a dangerous skid. Yet even when its time on the asphalt is over, its story continues, as recycled rubber finds new life in playgrounds, furniture, and soundproofing materials. Long before rubber meets the road, a tire's journey begins in the digital realm. This is where engineers meticulously craft every detail, from its cross-sectional shape and ply structure to the intricate tread pattern and precise rubber composition. Their objective is to strike a perfect equilibrium between conflicting demands: relentless grip, long-lasting durability, immense load capacity, and whisper-quiet operation. The final design is tailored to its specific purpose, whether destined for a high-performance sports car, a heavy-duty truck, or an everyday passenger vehicle. Each concept is then pushed to its limits through exhaustive digital simulations, a virtual trial that must be passed before physical manufacturing can ever begin. A single drop of white liquid holds the secret to enduring thousands of miles of brutal punishment. This milky sap, oozing from the bark of a rubber tree, is the fragile beginning of one of humanity's most resilient creations. In the heart of tropical plantations, the process relies on human hands. Skilled tappers wield sharp blades, etching precise incisions into the bark in a delicate dance between harvesting and preservation. A cut too deep severs the tree's lifeblood, silencing its flow and risking its survival within weeks. The white latex bleeds drop by drop, collecting in small cups with a quiet, steady rhythm. To prevent it from solidifying, the raw liquid is mixed with ammonia before its journey to a processing plant. Here it is concentrated, pressed into thin sheets, and carefully dried, transforming from a fluid sap into solid rubber. Yet, natural rubber on its own cannot withstand the rigors of the modern road. To achieve the required durability and resistance to abrasion, it must be blended with a far more stable, engineered counterpart: synthetic rubber, born from the world of petrochemicals. This material isn't harvested, it's constructed. Inside industrial labs, a process called polymerization forges powerful chemical bonds, linking small molecules like butadiene, styrene, or isoprene derived from oil and natural gas. The outcome is a durable, flexible polymer engineered to maintain its form under the most punishing conditions. With its superior strength, wear characteristics, and resistance to cold, synthetic rubber now constitutes over 60% of a modern tire's composition. It is this engineered core that guarantees consistent, reliable performance across tens of thousands of kilometers of unforgiving road. Its deep black hue is a deliberate illusion, a stark contrast to the pale material from which it is born. The tire, built to endure tens of thousands of kilometers, begins its life not as black, but as a humble off-white rubber. To forge a material tough enough for the road, manufacturers create a precise blend of ingredients. This recipe combines natural and synthetic rubber with carbon black, softening oils, sulfur, and a suite of specialized chemical additives. In the mixing chamber, over 30 different components are meticulously measured and combined. The addition of carbon black grants the material its signature color, along with crucial durability and resistance to abrasion, while softening oils ensure the rubber stays pliable across a wide range of temperatures. Other additives carefully tune the compound's physical nature, dictating everything from its melting point and curing time to its ultimate hardness. Once prepared, these ingredients are fed into a massive industrial mixer, where intense heat and pressure go to work. Within minutes, the elements fuse into a thick, jet-black rubber compound. But this is more than a simple blend. On a molecular level, the additives have reinforced the rubber structure, making it immensely stronger than its raw form. The transformed material is then pressed into thick sheets, which are rolled up and sent to a cooling section. While it doesn't yet resemble a tire, the core traits of durability, elasticity, and stress resistance are already being woven into its very fabric. The process of building a tire's inner structure starts with these thick sheets of black rubber. They are first passed through heavy rollers, flattening them into thin, uniform layers that are then carefully wound into spools. Behind the scenes, automated systems ensure that no hidden air bubbles or folds remain, as any imperfection could compromise the final structure. In the next stage, a layer of high-strength synthetic fabric is coated on both sides with molten rubber. A heated calendaring system applies exacting pressure and temperature, forcing the rubber to bond tightly with every reinforcing fiber. At the same time, ultrafine steel wires, deceptively thin but incredibly strong, are arranged in perfect parallel alignment. These wires are then bonded to the rubber under immense pressure, forming the tire's essential structural frame. This steel reinforcement is what allows the tire to hold its shape and perform reliably, even under the stress of high speeds. The entire operation is governed by advanced technology, with every detail monitored to create a product engineered for safety and unwavering performance across a wide range of driving conditions. Here, pliable sheets and woven steel are summoned to a single point. On this spinning drum, a new form will be born. With all components ready, from the airtight rubber layer to reinforcement fabrics and steel belts, the shaping process begins. These elements converge on a large rotating drum, where an automated assembly system initiates a complex sequence. Robotic arms move in perfect sync, following pre-programmed instructions to execute each task with immense precision. A centralized digital system tightly controls every parameter, from rolling pressure and rotation speed to the exact duration of each press. The entire setup can assemble dozens of tires per hour, all while maintaining tolerances within 0.1 millimeters, a near-perfect standard for the industry. Each rubber layer is applied by a servo-driven system, pressed tightly and aligned perfectly with the one before it. To prevent any overlap, wrinkling, or misalignment, force sensors and industrial cameras monitor every millimeter of the surface. This constant flow of image and pressure data allows the system to instantly adjust its rotation, force, and wrapping speed at each point of contact. As soon as the raw structure is built, the next phase begins, inflating the tire body with compressed air. Internal pressure causes the soft rubber shell to expand, conforming exactly to its intended shape. This marks the first transformation from separate materials into a unified, cohesive form. Pressure sensors and shape scanners monitor every subtle change during this critical expansion. If any deformation is detected, the system halts immediately for correction. In just a few seconds, the basic shape of the tire is complete, a raw but promising structure, ready for the final stages of its creation. A blank canvas of rubber is about to receive its defining features. This final transformation is what grants the tire its incredible endurance. On smaller production lines, the patterned tread that grips the road is sometimes attached in a separate step. Using a cold pressing method, this distinct layer is fused onto the raw tire body with a flat press, ensuring a firm bond before any heat is applied. In larger, more advanced factories, however, the tread is formed directly during vulcanization, an integrated process that is both more precise and cost-effective. The entire raw assembly is placed inside a heavy, two-piece metal mold that seals shut like a giant waffle iron. Etched into its interior surfaces are the intricate negative patterns that will define the tire's final design. As the cycle commences, the system heats the mold to between 160 and 180 degrees. Simultaneously, a flexible bladder inside the tire is filled with compressed air or superheated fluid. This creates immense outward pressure, forcing the softened rubber to expand and press firmly into every fine groove of the mold, perfectly forming the tread. This intense vulcanization process lasts between 10 and 15 minutes, depending on the tire's specific size and type. During this time, a deep chemical reaction occurs between sulfur and the polymer chains within the rubber. Molecular bonds are reinforced and locked into place, transforming the soft, pliable material into a tough, elastic structure. This single stage is critical, determining the tire's mechanical strength, heat resistance, road grip, and overall lifespan. Still radiating heat from the mold, a new tire's journey is far from over. While the tread is still warm, it is immediately ushered into quality inspection. Though it appears complete, a gauntlet of rigorous trials awaits before it can be certified for the road. The process begins with a geometric analysis. Beams of industrial laser light scan the entire surface, scrutinizing its roundness, center alignment, and thickness. Even the slightest deviation is enough to disqualify the tire from moving forward. Next, the tire is mounted onto a rotating spindle and inflated with compressed air to a pressure higher than its normal operating level. This intense test checks for air retention and structural integrity under stress, with any leaks or abnormal deformations being instantly flagged by the system. In more advanced facilities, X-ray technology is used to examine the internal structure, revealing areas invisible to the naked eye. This process allows for the high-precision detection of misaligned layers, hidden separations, or bonding defects. Only the tires that pass every single test are marked with an approval stamp. From there, they are moved to storage, ready to take on the road ahead, where speed, weight, and pressure demand nothing less than perfection. They carry us for hundreds of thousands of kilometers, only to be left behind. But they never truly disappear. Each year, billions of these discarded rings of rubber accumulate in vast landfills or are simply forsaken in the wild. Unlike organic matter, a tire stubbornly resists the passage of time. Its complex chemistry, a blend of synthetic rubber, mineral oils, and heavy metals, creates a fortress of durability that poses a lasting threat to the health of our soil, water, and air. If set ablaze outside of a controlled facility, they unleash a toxic plume of dioxins and benzene into the atmosphere. But a slower, more insidious danger emerges when they are left to the elements, as wind and rain steadily erode them, carrying a silent tide of microplastics into our waterways and eventually into the food chain. To confront this mounting challenge, advanced recycling technologies are now breathing new life into old tires. The transformation begins with a powerful mechanical process where immense shredders tear the waste tires into fine rubber granules. These particles are then subjected to a careful treatment of heat, pressure, and chemical agents, designed to partially rejuvenate their original resilient properties. This reborn rubber finds its place deep within the structure of a new tire. It is carefully integrated into the inner layers, like the liner or cushion, safely away from the direct, abrasive contact with the road surface. While this reclaimed material constitutes just 10 to 20% of a new tire's total mass, its inclusion marks a pivotal change. It is a small but vital step toward lessening our reliance on petrochemicals, curbing a mountain of waste, and slowly transforming an environmental liability into a circular, sustainable resource. We see only black rubber against gray asphalt, but in that single point of contact, an entire science of motion unfolds. Beneath what seems to be a simple outer layer is a sophisticated web of technologies, each engineered with microscopic precision. An entire world of complex design hides just out of sight, a testament to the detail required for modern performance. Though it is just one component among thousands, the tire forges the solitary connection between a machine weighing several tons and the surface of the road. It is the final, crucial interface where human engineering meets the physical world. In this narrow space, the fundamental forces of movement, safety, and performance are born. And so a familiar object, often overlooked, reveals itself as a quiet monument to the ingenuity hidden in our daily lives.